Welcome to problem number 4. And this problem is very unique from the other problems because what we're going to do is we're going to actually look at a system and quantitatively figure out, is the system at equilibrium? So when we did Le Chatelier's principle, one of the examples was one of the sides, whether it was right or left, that really doesn't matter. So let's say the left side was colorless and the right side was brown. Then what you would see is sort of an intermediate color between dark brown and colorless, and that would be equilibrium. But what happens, qualitative is fine, but if you're trying to be really analytical, then moving towards quantitative is a little bit better. So there will be questions where it's not so obvious which way it's going to go. So most of the problems we've done, then you're given reactants, and then it's obvious the reaction needs to proceed to the right to make products, right? You can't go down from zero. So if the products start from zero, they can only go up. But then if you're given a question where everything is present, so you're given concentrations for all the reactants and all the products, then you can do a calculation to figure out which direction the reaction is going to go, or if it is truly at equilibrium. So these questions will be worded a little bit differently, so hopefully you'll be able to pick out what you're trying to do here. Okay, so it's like a snapshot. So someone's taken a chemical picture and determine the concentration of everything inside the system, all the reactants and all the products. Okay, so you're given these values, so you'll be given you'll be given concentration values, and then you just plug them into the equilibrium law expression and see what value you get. So since it's based on reaction data, we call it a trial value. So that means, like I said, it's like a snapshot at a certain period in time in the chemical reaction and what's going on. Is it equilibrium? Is it shifting to the right or favoring the forward direction? Or is it favoring the left or the reverse direction? So because an equilibrium law is products divided by reactants, the answer to division is a quotient. So we call it the reaction quotient. So really it literally has to do with the type of math you're doing and what your answer is called. That's why we call it the reaction quotient. You can just use capital Q and that's fine. So when the next section, when we do solubility equilibrium, our equilibrium laws will only have multiplication. So instead of a reaction quotient, we're going to calculate a reaction product, okay? So it's just sort of semantics, has to do with the math. So what you're going to do is calculate a Q value. So how do we do that? So Q is calculated exactly the same way as KEQ. So still products over reactants. The coefficients would still be exponents. So it's calculated the same way as KEQ, and then you're going to compare them. If they're equal, then that means equilibrium. And then if it's not equal, then we have to figure out what's happening. So in these questions, it seems like you're given almost too much information. You're going to be given a KEQ value. You're going to be given concentrations of everything. So then it's like, well, okay, but what do we do? And it won't say initially it's this, allowed to reach equilibrium this. It'll just give you the numbers. So what you're going to do then is sub it into Q and ask to compare it to KEQ value. No ice. So no ice. Put all of those exclamation points there, because if you build an ice table and you solve for the equilibrium concentration, that's forcing it to be at equilibrium. And that's not what we're trying to do. We're trying to decide, is the system at equilibrium? Okay. So I'll show you with the example, like how the wording's different and hopefully how you can decide that this is the kind of question you're going to do. Okay, but let's talk a little bit about comparing Q to KEQ. So once you calculate your Q value, if they are equal, then the system is at equilibrium. But when the Q is greater or less, then you have to, again, think about what's happening really essentially with the fraction. So if Q is greater than KEQ, so now our system is, whatever's happening in our system is not at equilibrium and Q is too big, which means that the value needs to get smaller. So if the value of Q needs to get smaller, then remember in our fraction, if you have 1 over 4, it's 0.25. 4 over 1 is 4. So if you want your number to get smaller, then the bottom of your fraction needs to get bigger. And what's at the bottom of the fraction? Always, when you're doing equilibrium law, the bottom of the fraction is always reactants. So that means the reactant concentration needs to increase in order for our Q value to get smaller so it can reach more towards being equal to KEQ. So the reactant concentration needs to increase, the product concentration needs to decrease, which is a shift left. Okay, so shift left, again, if you don't like directions towards the reactants, the reverse direction is favored. All of those are fine and they mean the same thing. Okay, then if Q is less than KEQ, now our number needs to get bigger. So how does our number get bigger? The top of the fraction has to get bigger. And always what's at the top of the fraction? That's where the products are. So if the products need to increase, then that means it has to shift right towards the products, or forward direction has to be favored, whichever you prefer. Okay, so let's do a problem. So when 3 moles of HI, 2 moles of H2, and 1.5 moles of I2 are placed in a 1 liter container, will a reaction occur? So sometimes the question will say, will a reaction occur? Sometimes the question will say, is the system at equilibrium? On the review sheet I was just looking at, the question said, it was like determine the direction in order for equilibrium to be established. So sort of giving it away, it's not at equilibrium. So which way does it have to go? So those are the kind of things you're going to do. So here our reaction is, sorry, but PowerPoint doesn't like the equilibrium arrow. So this is the reaction. So we're given HI, which is the product. And then we're given H2 and we're given I2, reactant. We're also given a KQ value. So again, you're given so much information. It's like, oh, I'm going to do ice, but where does it go? Does all of these have an initial equilibrium value? You don't know. It doesn't say allowed to reach equilibrium. What are the equilibrium concentrations, like problem number 2 and 3 did, and number 1. Okay, so you're not making an ice table because that's going to force it to be at equilibrium. And the question is saying, is it at equilibrium? And then which direction will take place. I think your textbook calls it, the net direction, which is just the same thing. Does it go forward or does it go reversed or right or left? It doesn't matter. Okay, so what are we going to do? We're going to calculate our Q value, which is exactly the same as, or calculated the same way as the KEQ. So we are given moles. It is 1 liter. So dividing by 1 does not change. So you've got 2 molar H2, 1.5 molar I2, and then 3 molar HI. Okay, so again, we're given concentrations of everything. So that's unique. So you write the Q expression. So Q, remember, is still products over reactants. And it includes the coefficient just like KEQ. Because that's what we're trying to see. Sorry, it's supposed to be a K. Are they the same or are they different? So you plug in the numbers. Again, no ice, no ice. If you do ice, that forces it to be at equilibrium, and that's not what we're trying to say here. In this snapshot, is the system at equilibrium? Okay, so the HI concentration is 3 squared because of the coefficient of 2. H2 is 2, 1.5, and I2 is 1.5, which is 3. So now the KEQ we were given up here is 50. So that is much less than KEQ. So now our equilibrium, it's not at equilibrium because Q is less than KEQ. And so if Q is less than KEQ, the number needs to get bigger. It needs to get closer to 50. And again, how does it do that? You have to think in terms of math. If you want a number to get bigger, you need the top of your fraction to get bigger. How does the top of the fraction get bigger? Shifts to the right, where the products are. So let me I'll write that. Okay, so let's say, let's see if I can get a different color here. Let's say you're going to, let's say this was a question. Okay, so you would get, if you had to calculate concentration, you would get marks for that. You would get marks for the equilibrium law. You would get marks for the number. So in these questions, like say if it was a traditional test, I would say things like the math is out of 3, 3 or 4, but the explanation is also out of whatever. Okay, so you need to say how Q compares to KEQ, which direction it shifts, and why. So when you are doing an explanation, whether it's Q in this section or Q in the solubility section, make sure that you are providing enough information in your explanation. How is Q compared to KEQ? How does it shift, and why? Okay, so good luck with these questions. Let me know if you have any, and I will also post review questions for next week's quiz or assignment. So remember, I'm going to split this huge unit up into 2. So we're going to do one quiz for this section, the intro section, and then we'll do a separate solubility quiz. So if you have somebody else's notes from another year, they're